In 1911, a physicist performed an experiment that led him to the discovery of the nucleus. Ernest Rutherford's observation of this tiny collection of particles opened the door to momentous scientific breakthroughs, including, but not limited to, the field of nuclear power. I'm Rich Burnett for Wondrium, and in this episode of Perspectives, 4 experts delve into the fascinating world of nuclear reactions and the benefits and risks of nuclear power. We start now with a quick look at nuclear energy consumption, and then we dive deep into the subatomic realm where the real magic happens.
Currently, nuclear fission provides about 11% of the world's electricity, which is just under 6% of the world's total energy consumption. This is about 300 gigawatts from 450 nuclear reactors worldwide. The global distribution of nuclear power is more limited than other energy sources. Anyone can burn coal, but you have to have a high level of technological infrastructure to build and maintain a nuclear reactor, and currently only 31 countries have that ability. The US is the largest user of nuclear power, accounting for about a third of it, and this provides 20% of all US electricity. Other countries that are large users of nuclear power are France, Russia, Korea, and China. And actually, for 9 countries, mostly in Europe, led by France, nuclear power provides 40% or more of their country's electricity. So, nuclear power provides an important but modest contribution to world energy supplies, at least compared to the fossil fuels. Let's take a look at what we think is going on at a subatomic level within the generation of nuclear energy. During fission and fusion, a small amount of mass is converted into binding energy, some of which is released as radiation that we can use as a source of heat. Let me start by going back to the example of that helium atom. The nucleus of most helium atoms contains, as I said, 2 protons and 2 neutrons. And we know the masses of individual protons and neutrons. A proton is 1.00728 atomic mass units. A neutron is 1.00866 atomic mass units, slightly larger. So if you added 2 protons and 2 neutrons together, you would get, are you adding this up? 4.0319 atomic mass units. I'm sorry for all the decimal places, but I need to include them to make a point here. Okay, 2 protons, 2 neutrons, 4.0319 atomic mass units. However, if you look at the nucleus of a helium atom, that's not what you get. Sure enough, you have 2 protons and you have 2 neutrons, but the mass is less. It's now 4.0015 atomic mass units. This is less than the mass of the separate protons and neutrons. And this is very strange. This is one case where the whole is actually less than the sum of the parts. The difference between the two, 0.0304 atomic mass units. This is a little less than 1%. So this is strange. You take 4 particles, you put them together, and you suddenly lose 1% of their mass. Where did that missing mass go? Well, it went into the energy needed to bind the particles together. And you could calculate exactly how much energy that is. After all, energy is conserved. And we know that Einstein's equation, E equals mc squared, will tell us how much energy we get from the mass. The missing mass turns out to be about 5 times 10 to the minus 29th kilograms. That's incredibly small. But when we multiply it times the speed of light squared, which is 3 times 10 to the 8th meters per second squared, that's a very big number, we now get 4.5 times 10 to the minus 12 joules. That's for each helium atom. So joining the neutrons and the protons to make the helium nucleus converts the mass into energy. A lot of energy. 1 gram of helium made from fusion, that's about the weight of an almond, generates the same amount of energy as you get from burning 23 million grams of coal, 23 tons of coal, from something the size of an almond.
A nuclear power plant is similar to a coal-fired plant in the sense that both use closed-loop steam cycles to spin turbines. The big difference is simply that the source of energy used to produce the steam is different. It's chemical energy for a coal-fired plant, nuclear fission for a nuclear plant. Nuclear fission, the splitting of atomic nuclei, depends on the unique behavior of certain heavy elements called fissile materials, which are used as nuclear fuel. By the way, the word fissile means easily split. And so a fissile material is one that's capable of sustaining the chain reaction associated with nuclear fission. The most common fissile material is uranium-235. When the nucleus of a U-235 atom is struck by a neutron, it breaks apart, releases energy, and emits a few free neutrons. If a sufficient quantity of this material is assembled in one place, the neutrons emitted by the fission of one nucleus will encounter adjacent nuclei, causing them to split, release energy, and emit more neutrons. As this process continues, progressively more free neutrons cause the fission of progressively more nuclei, and the result is a nuclear chain reaction, self-sustaining fission. If this chain reaction is controlled, we have a very potent source of energy. If it's uncontrolled, we have a nuclear explosion. But how does this reaction get started in the first place? Well, uranium-235 experiences a small amount of spontaneous fission, a natural form of radioactive decay that releases a few neutrons. So we really only need to assemble a critical mass of uranium-235, and this natural emission of neutrons will set the nuclear chain reaction in motion. Nuclear fuel is prepared for use in a reactor by molding uranium into small pellets, which are then sealed inside metal tubes to create fuel rods. The tubes are made of zirconium alloy, used because of its corrosion resistance and low neutron absorption. The purpose of the tube is to contain the uranium pellets so fragments can't break away and contaminate the reactor coolant. The fuel rods are assembled into bundles of about 200 each, like this. And about 150 such bundles are then combined to form the reactor core. These holes in each bundle allow for the insertion of control rods, cylindrical bars made of boron carbide, a material that's particularly effective at absorbing neutrons. When the control rods are inserted into a fuel bundle, they absorb enough free neutrons to prevent the fission reaction from sustaining itself. Thus, they keep the nuclear reaction from getting out of control. When they're withdrawn, they allow the reaction to proceed.
How do we turn heat into electricity? Well, we have to obey the three laws of thermodynamics. The three laws of thermodynamics are you can't win, you can't break even, and you can't quit. Or, what it really means is you can't win, energy is conserved. You can't break even, which says that entropy increases or the amount of useful energy decreases, and you can't quit. So what do? We use the heat to boil water, to turn a turbine, to spin a generator. And we need a cold sink to dump the waste heat into. That cold sink can be a river, a lake, or an ocean, or we can use a cooling tower. Cooling towers get rid of some of that waste heat by evaporating a lot of water, and that peculiar shape of cooling towers that you see on the skyline is there to maximize the airflow. And the thermodynamic efficiency is about 1/3, and so that means that 2/3 of the energy has to be dumped into rivers, lakes, or oceans, or up the cooling tower. And that's due to the limitations of thermodynamics. We use the same process for coal, natural gas, and nuclear power to turn heat into electricity. What kind of reactors do we use today? We use light water reactors, so that's regular hydrogen, not deuterium. The water is both the moderator and the coolant, and these were originally developed for the US Navy under the guidance of Hyman Rickover. There are two general types of light water reactors. There's a pressurized water reactor, where the water is under high pressure so it doesn't boil. Higher pressure means a higher boiling point. And so the primary cooling water then has to transfer its heat to a secondary water system. The secondary water system is allowed to boil and turn a turbine. The second kind of light water reactor is the boiling water reactor, which is just what it sounds like. The primary water is allowed to boil, and we use the steam from the primary water system to turn the turbine, and so it doesn't need a secondary water system. Then there's the pressurized heavy water reactor, the CANDU plant in Canada. So it uses a heavy water moderator, so that's deuterium oxide, and a heavy water primary coolant, and so it can use unenriched uranium, and then the heavy water transfers its heat to a light water secondary system, which then boils and turns the turbine. There's also a water-cooled graphite moderated reactor. And so that's similar to Fermi's original reactor, so graphite moderated, but now it's water cooled. It can also run on natural uranium, so this is the Chernobyl type reactor, and it's built for power and for producing bomb-grade plutonium. The pressurized water reactor is the most common reactor in use today. It uses pressurized water at 150 atmospheres and about 300 degrees centigrade, which is about 600 Fahrenheit, as the coolant and the moderator in the reactor vessel. It's a closed loop. We don't let that water escape. There's a reactor pressure vessel, which is about 40 feet high, it's about 15 feet in diameter, and it's made of 8-inch thick steel. The primary water system then transfers its heat to a secondary water loop in something called a steam generator, and then it has a containment building with concrete and steel to contain everything inside of it. The pressurized water reactor then, the non-nuclear part, the steam from the secondary water system turns the turbine turns the generator. There's a condenser that condenses the steam to make the low pressure side of the turbine, and we need a cooling source for that condenser, which, as we said, can be an ocean, a lake, a river, or a cooling tower.
Now, it's important to recognize that from a macro perspective, the advantages of nuclear power are considerable. Nuclear plants can operate at max capacity for extended periods of time, so they're very effective at meeting base load. Although nuclear fuel is a non-renewable resource, there's enough of it in the Earth's crust to last for centuries. More importantly, properly contained nuclear fission produces minimal air pollution and no CO2. In the first decade of the 21st century, a growing appreciation for these advantages, coupled with post-9/11 concerns about our dependence on energy sources from unstable regions of the world, led to a resurgence in enthusiasm for nuclear power, both in the US and abroad. Many new power plant construction projects were initiated, and there was talk of a nuclear renaissance and of nuclear power as a major component of a new environmentally friendly power generation system. And then came the 2011 Fukushima power plant disaster, throwing the nuclear industry back on its heels once again. The Fukushima incident was triggered by a magnitude 9.0 earthquake off the coast of Japan. Initially, the plant's safety systems worked exactly as they were supposed to. In all 3 operating reactors, control rods were inserted into the reactor cores to shut down self-sustained fission, and emergency generators were switched on to power the cooling systems. This is an essential aspect of nuclear safety because even after the control rods stop the self-sustaining fission reaction, the reactor core continues to produce tremendous heat for many hours because of continuing radioactive decay. Thus, it's critical to continue coolant circulation for several days after a shutdown. Tragically, at Fukushima, 50 minutes after the earthquake, an earthquake-induced tsunami overtopped the plant's protective seawall and flooded the facility, causing the emergency generators to fail. The plant's backup battery system immediately took over, but when the batteries went dead the following day, there was nothing to prevent all 3 reactor cores from melting down. In a meltdown, the nuclear fuel elements exceed their melting point, causing fission products to enter the coolant water and greatly increasing the possibility of a radioactive release from the containment vessel. At Fukushima, the result was a humanitarian, environmental, and economic catastrophe. Fukushima effectively ended the nuclear renaissance, while reminding the world that despite stringent regulations, exacting engineering codes, and extensive redundant backup systems, nuclear accidents can still happen. And when they do, the consequences can be dire indeed. Beyond the potential for nuclear accidents, the long-term viability of nuclear power is also plagued by the still unresolved challenge of nuclear waste disposal. This challenge is exacerbated by the high level of radioactivity in the products of nuclear fission. Several of the new elements created when uranium nuclei split apart have half-lives of over 1 million years. These serious challenges notwithstanding, nuclear power is not going away anytime soon. In 2012, the U.S. Nuclear Regulatory Commission approved the construction of 4 new reactors at existing power plants. China, India, and South Korea are building new reactors as well. France currently generates 75% of its power with nuclear fission. And even in places where nuclear power has fallen out of favor, the immense capital investment in existing plants provides a strong incentive to keep them in operation for as long as possible.
But the very obvious question remains: can nuclear fusion be not only initiated, but controlled? Could we somehow tap this incredibly powerful reaction the way that Fermi did with fission? It's a tantalizing prospect. Just imagine if we could tap nuclear fusion in a controlled way, not using fission bombs to initiate fusion reactions that are over in less than a second, but more elegantly conducted reaction. One in which hydrogen isotopes are fused into helium and the energy of that process is tapped. We would have power plants that use the most abundant element in the universe as fuel and produce harmless, stable helium as waste that simply floats into space. But the problem that we run into is that even deuterium-tritium fusion, which is the easiest type of fusion reaction to start, requires temperatures about 40 million kelvins to sustain. The energy needed to overcome the coulombic repulsion of the 2 hydrogen nuclei is just so monstrous that we can't run fusion in a power plant the way that we can do it in a bomb. There must be something fundamentally different about how a fusion reactor is designed if it's going to be practical for power generation. We have to find a way to run the same nuclear fusion reaction at drastically lower temperatures. We have to create a type of cold fusion. The quest for controlled nuclear fusion started about the same time that the thermonuclear weapon, or H-bomb, research began. Attempts to use magnetic fields to create containment systems capable of generating high pressures have been employed, and physicists call this the pinch technique. Although many of these types of systems have been able to contain high-energy hydrogen isotopes, none can create the conditions right for nuclear fusion. Perhaps the most well-known story of controlled nuclear fusion is the so-called Fleischmann-Pons experiment in 1989. This experiment was a roller coaster ride of emotion for researchers in the field, as it raised the world's hopes for clean, cheap fusion power just before dashing those hopes nearly permanently. In 1989, Martin Fleischmann and Stanley Pons were conducting electrochemical research at the University of Utah, and they believed they were onto something. They had constructed a very simple device that both men believed would change the world. Fleischmann and Pons created an electrochemical half cell using a platinum electrode submersed in what is known as heavy water, or water containing deuterium instead of hydrogen. Of course, the product of this half reaction is deuterium itself, which should effervesce and bubble out of the system as hydrogen gas. But Fleischmann and Pons had detected deuterium in the platinum electrode itself. Not a particularly surprising claim, since hydrogen gas interacts with platinum very strongly, adhering to its surface. But what they claimed next started a storm of scientific controversy that's the stuff of legend. The two published a paper claiming that they had detected heat in excess of any expected chemical reaction that would go on in their setup. In one of the most famous rushes to press in all of scientific history, Fleischmann and Pons let their excitement and the pressure to patent their potentially world-changing development hurry the publication of their research. Not long after their publication, scientists around the world began trying to duplicate their results. There was just one problem: no one could. Clearly, Fleischmann and Pons had been wrong. The resulting fallout in the professional and popular media was swift and intense. Many popular magazines and newspapers decried the entire situation as a debacle, and both public and institutional support for the concept of cold fusion was crushed. So the work of Fleischmann and Pons is now taught not as an example of nearly making the greatest discovery in the history of mankind, but instead as a cautionary tale of what is known as pathological science, a term used to describe a situation in which a scientist, originally working in good faith using the scientific method, abandons objectivity and gives in to what is known as confirmation bias. To this very day, fusion research is limited, in part due to the bitter taste left in all our mouths after the infamous experiment in 1989. But that doesn't mean that humankind will never find a way to harness this awesome reaction. It simply means that we may have to wait a generation or two longer. Who knows?
Thanks for watching. If you'd like to learn more about the topics in this episode, the full list of series that these clips came from is in the description below. You can watch them all now on Wondrium.